Hello and welcome to this video where today we're looking at the photoelectric effect as part of the Turning Points option for A-level physics for AQA. So much of this is going to be a revision of what you did in year one. So really we're going to revise this. We're going to look at, again, stopping potential, some certain definitions. So this should be really quite familiar to you. So we're going to start off by looking at thermionic emission. So if you remember from what we've looked at thermionic emission, what we can do is we can basically take a metal. So metals contain conduction electrons, and what we can do, conduction, and what we can do is if we give these electrons enough energy, then we can free them from the surface of this metal. And the way we did this with thermionic emission is we basically heated this wire up, and we did that by connecting it to a source of potential difference. So the current flowed, because this has resistance, the wire gets hot. That energy is transferred to all of the particles inside here, so the electrons gain kinetic energy, and if they gain enough energy, then they're able to break free of the metal, and then we were able to, for example, calculate the specific charge of these things. And that was the process of thermionic emission. The photoelectric effect is in essence exactly the same thing. We supply energy to these electrons inside a metal, and so we're able to free them from the metal. It's just that instead of using heat, we use light. So if you remember, this is your photoelectric effect. You take light, you shine it onto a metal such as zinc or sodium, and then what you find is that, provided that the light is of sufficient frequency, then you end up with electrons being freed. And when the electrons are freed, they're just given a different name, so they're called photoelectrons. And the reason they're photoelectrons is because they've been freed because they've absorbed energy from light. Now, when it comes to looking at light, one thing that's really important is the intensity of light. And we use intensity for a few different bits and pieces, but it's probably good to go back and recap it again. So intensity, it really is the amount of energy per second hitting an area. So if we write that as an equation, we've got intensity is equal to the energy per unit time per area. And if we write the units of those, that's joules. Time is in seconds, and area meters squared. Now we know that joules per second we can also call a watt, so that's basically equal to a watt per square meter, like that. So the units of intensity are these things, and what it really says is this relates how much energy is incident per second on a certain area. So we can change the intensity in a couple of ways. What's going to be important for us is looking at the intensity on a certain area. So if, for example, we consider this area here, all of this light energy, all of the energy coming from here is being shone onto this metal, and it spreads over the whole of this surface. So in some respects you can imagine that the intensity is fairly low compared to if we move the metal to here, for example. The same amount of energy is incident on the surface, but it's now spread over a smaller area. If the area is smaller, then the intensity is bigger. So that's really what we mean by intensity. The other way we could do it is basically to increase the amount of energy per second that is hitting this, and we could do that basically by making our lamp more powerful. So you could have a 100-watt bulb instead of a 60-watt bulb, and basically it means that in everyday terms, the light that's hitting this surface is brighter than it was than if we used a 60-watt bulb. So that's intensity and what the photoelectric effect is. A bit of revision now. So this was an experiment that was done towards the end of the 19th century. And these are the observations that were seen. So people did lots of experiments looking at lots of different metals, and they always found the same results. They found that the photoelectric effect only happens if this light is above a certain frequency for a particular metal, and they call that the threshold frequency. They found that the photoelectrons, so these electrons here, so when lots of electrons come out of here, they have a range of kinetic energies. So they're all travelling at different speeds, but there's always a maximum value of the kinetic energy. And that depends upon the type of metal you've got and also the frequency of the light. So, but there's always a maximum kinetic energy. They also found that if you increase the intensity of the light, so basically we're increasing the brightness of this light or the energy per square meter, that increases the number of electrons emitted. So the number of electrons depends upon the intensity of light, and photoelectric emission occurs immediately. So as soon as we switch this light on, provided the frequency is high enough, you start to see electrons being given off straight away. So people went, okay, so here what we've got is we've got a set of observations from an experiment. Let's try and explain them. And we know, basically because of what Maxwell did and what Hertz did, that light's a wave. So if we look at our wave theory, then because a wave is essentially a continuous thing, if we shine it on the metal, all of this energy is spread out evenly over this metal, and so it doesn't matter about the frequency. What should happen is all of these electrons gain energy from this light, and so electrons should be emitted no matter what frequency we've got. It doesn't really matter. It simply depends upon how much energy is being supplied to these things. If we did change the frequency, if we made the frequency smaller or made the frequency lower, it simply would take longer for photoelectric emission to occur. And the kinetic energy should increase with intensity, and that kind of makes sense as well if you think about it, because if we increase the intensity, we're increasing the amount of energy that's incident on this metal, and if we do that, these electrons would gain more energy, and so they'd move faster, basically. So, but this theory contradicts what's seen. So that was the big issue. So before we move on, just a couple of definitions, because the exam board like definitions. There are really a couple. The work function is a definition that gets asked a lot. The word minimum is very important because it is a minimum amount of energy that's needed to remove an electron from the surface. It can take more. So for example, this electron here has to get to the surface first, so that requires energy, and then it needs the work function amount of energy to get away. So that takes more energy than, for example, this electron here that's on the surface. The threshold frequency is the frequency of light, the smallest frequency of light that causes photoelectric emission to happen. So if we have light below of frequency below the threshold frequency, you'll never ever see this happening. If you have light above the threshold frequency, then you will. And finally, monochromatic. You see the word monochromatic a lot. Mono simply means one. Chromatic basically means colour. So this means one colour. And since frequency is related to colour, monochromatic means light that's got only one particular frequency. So what we really want to do is we want to explain these observations here. And wave theory just doesn't cut it. So what we're going to do is we're going to look at basically how it was explained. And again, this will be familiar from last year. There's an extra little bit at the bottom. But it basically fell down to Albert Einstein to explain this. And what he did is he basically took an idea that Planck came up with. So he knew, for example, Planck had explained that energy comes in packets, which he called quanta. So you have a quanta, the smallest part, the smallest discrete part of electromagnetic radiation, and the energy of this quanta is related to the frequency. And that kind of gives you a hint that because the experiments were looking at how frequency changed, it kind of gave Albert Einstein a hint that frequency and energy are related, and so therefore you can use Planck's quanta idea. So Einstein basically said this. He basically said, okay, I'm going to assume light's made up of these small packets, but I'm going to call them photons instead. And these photons are these quanta that Planck was going on about. And he took Planck's idea that the energy of the photons are proportional to the frequency of the light. So that equation here that we've just written down. And what he said is, right, okay, if I'm going to treat these quanta things as like particles, then what must happen is a single photon interacts with a single electron. I can't have one photon coming in and interacting with, say, this electron and this electron. So you have one photon interacting with one electron. And what I need to do is I need to provide enough energy with one photon and give that to one electron, and that energy has got to be at least equal to the work function, because if it's not, then I'm not giving this electron enough energy. If I do give it enough energy, then this electron can basically be freed from the metal. Now, one really important kind of new thing is we're going to think about how much energy it actually needs, this thing needs, in order to gain enough kinetic energy to move away. Now, if we heated these things up a lot, then we'd end up with thermionic emission. And because these things are basically at room temperature, then they've got kinetic energy anyway. So you might go, well, actually, if this thing's warm enough, then the kinetic energy would be enough to overcome the work function. But at room temperature, that's not. We don't really have to think about the kinetic energy of these conduction electrons, because the kinetic energy of a conduction electron is really, really small compared to the work function when we're talking about room temperature type temperatures. That means that the electrons need to absorb at least the work function worth of energy in order to be freed. So what we're really saying is we don't have to consider the starting kinetic energy of these things at the beginning. So that's what the exam board are now saying, that you've got to assume that the kinetic energy of these things is negligible compared to the work function. And if you do that, you don't have to include the kinetic energy in any equation, at least the kinetic energy that these things have got to start off with. So what Einstein did is he basically said, okay, this effect only happens above a certain frequency, and that makes sense because if E is equal to HF, what we're basically saying is this only happens above a certain energy, and we know that because that's called the work function. Increasing the intensity increases the number of electrons. Well, if we increase the intensity, that simply means we've got more photons. And if we have more photons, because we know that one photon interacts with one electron, if we've got more photons, we'll have more electrons being emitted. So that works. So a good way to write this is to say that the current increases. So current is the rate of flow of charge. So if we've got more electrons, then we have a greater current coming from this metal surface. And photoelectric emission occurs as soon as light hits it. Well, even if we've got one photon that comes in like this and hits one electron, and provided it's above the threshold frequency, then this electron will basically be freed straight away. So this photon theory basically agrees with this experimental prediction or experimental observation here. So the final one, looking at a range of energies, well, we know this here, and we know that the work function is the minimum amount of energy it takes to free a metal. So any energy that's left over, so if the energy of the photon is much bigger than the work function, then any energy that's left over is going to be in the form of kinetic energy. So what we can do is we can say the energy coming in, which is equal to HF, so that's energy coming in, is equal to the amount of energy coming out. And that's the energy is used up for two things. First of all, it's used up to actually overcome the work function, so that's thing here. And then anything that's left over is the kinetic energy. Now this makes sense because this therefore explains the maximum kinetic energy, because for monochromatic light the frequency is all one value, which basically means that the energy is at a set value. This thing, the work function, is a minimum value, so therefore that means you have a maximum value left over for the kinetic energy. If actually it takes more energy to get out, then the kinetic energy that is the energy that's left over to be kinetic energy is going to be less. And actually, if this electron is really deep inside here, it's going to take all of the energy that the photon supplies to actually get it to the surface and then overcome the work function, in which case the kinetic energy is zero. So we can actually say that the kinetic energy will be between 0, and that'll happen for a electron that's really deep inside this metal, and the maximum kinetic energy, EK max. So there is a maximum kinetic energy simply because of where the electron is and the fact that there is a fixed amount of energy coming in with these photons. So Einstein managed to actually come up and explain all of these in terms of photons. So what we really need to do is we need to be able to measure these things. And last year, in particular, you looked at this particular graph. You had the kinetic energy here, you had the frequency here, and what you can do is you can measure the frequency, and you can measure so you can change the frequency and you can measure the kinetic energy, or the maximum. So this is the maximum kinetic energy that's basically being transferred to these electrons. And you can plot a graph like this, and every single time you find out that the gradient is h, and the reason it's h is because you take this equation here, so you've got E equals hf, so it's the same equation we've just written down, which is this one, and you rearrange it like so. We rearrange it so that's rearranged to look like this. So we rearrange it so the kinetic energy is equal to hf minus phi, and if we compare that to a straight line, y equals mx plus c, then what we can see that is if we plot the kinetic energy on the y-axis and we plot the frequency on the x-axis, then the gradient is always h no matter what we do, and the y-intercept always gives us the y-intercept gives us minus the work function. And so the red line shows us what happens if we've got something with a lowish threshold frequency, and if we draw a line that's like this is a metal that's got a higher threshold frequency, so it's got a higher work function, but the gradient is still Planck's constant. Now, measuring the kinetic energy is a little bit tricky, but we can do this now because we've met equations that now allow us to do this. So this is a circuit that allows us to do it. We've got a power supply here, a potential divider here, and the exam board specifically say that you need to know how to measure these things using a potential divider. We've got a voltmeter, we've got an ammeter, which is actually going to be a micro ammeter here, and here we've got a photocell. And a photocell simply consists of a bit of metal on one side, on this side here, and a bit of metal on that side really, and this is the metal that we're interested in looking at the photoelectric effect with. So if we zoom in a bit, we've kind of got a metal like this, we've got another bit of metal over here, and this is our cathode, so this is where the electrons are going to come from, so that's why it's called a cathode, because it's going to give out electrons. And our anode's over on this side, and it's all contained within a vacuum because we don't want the electrons to be stopped or absorbed by any air nuclei or any air atoms. So what we can do is we can basically switch this thing on, and well, what we can actually do first of all is shine light onto here, and what we'll see is that electrons are freed and they will travel across here, and they'll all travel with a range of speeds, but there'll be a maximum speed because there's a maximum kinetic energy. We can then turn this on, and what we can do and what we'll see is that actually we make our cathode a bit positive. Now, and this is again one of those things the exam board need you to know, if we make the cathode slightly positive, then the electrons are going to require a greater amount of energy to actually be emitted from this cathode, because if you think about it, there's now an electric field that's going in that direction, like that. Electrons feel a force from an electrostatic field in the opposite direction to the electric field lines, so they'll feel a force backwards, so they'll actually be attracted back to this thing. So not only will they need amount of energy to overcome the work function, to get to this side over here they'll need a certain amount of kinetic energy, otherwise what will happen is they'll get so far and the acceleration, which is always in this direction, so acceleration is always in that direction, eventually they'll stop and they'll just go back to the plate. So what we do is we start off with a low potential, so a low charge on this thing, and we'll see electrons going from this side to here, and that'll form a current which we can measure, and then we gradually increase the potential difference, or gradually across here, so we increase the potential of this thing by changing the value of our potential divider. And as we do that, what we'll see is that the current decreases, and then as soon as it gets to zero, then we can measure the potential here. So this is called the stopping potential. Now, the reason this is important is because if you think about it, the amount of work done by the electric field between here and here is equal to E times V. So the stopping potential is the potential at which the electrons, or at which the current just becomes zero. So the amount of work done to stop those electrons that have got a maximum kinetic energy is equal to E times Vs, where Vs is our stopping potential, and that's equal to EK max. So what this really means is we've now got a way of actually measuring this. And then what we could do is we could shine light of a different frequency onto here and then just repeat the process and keep going, and we can plot a graph that looks like this. And if we do that, it's essentially the equivalent to this. So again, we've got a straight line. Instead of EK, we've got this thing here. So if we look at this, we've got E times Vs, that's equal to hf minus our work function again. So if we look at this, y is plotted on here, but we only want the stopping potential. So what I'm going to do is divide by E. So the stopping potential is equal to h over E times the frequency minus the work function over E. So I've just divided through by the charge of the electron. So if I plot the stopping potential on the y-axis here, and I plot the frequency on the x-axis, then the gradient is equal to h over E, this thing, and the y-intercept is now equal to the work function divided by E. So it's a very slightly different graph. The gradient will always be the same. So if we have a metal with a higher threshold frequency, again, we'd get a line like this. The gradient would all be the same, but instead of it just being Planck's constant, it's now Planck's constant divided by the charge of the electron. So the exam board specifically want you to be able to explain how you would use this circuit, what graph you would get, and therefore work out, for example, Planck's constant again. So in terms of significance, the reason this is significant is because Einstein basically showed that light is made of photons. It was the only way that you could actually explain the photoelectric effect. He took the idea that every photon carries energy that's proportional to its frequency from Planck, and he basically said that what we can really do is we can now consider this thing to be a massless particle. So what this means is that light's got this dual wave particle nature. It's a particle in the photoelectric effect, but it's a wave when it undergoes refraction and diffraction. And in another video, we'll have a look at wave particle duality and how you can apply it to things like electron microscopes. So, but this thing is again one of those things that the exam board needs you to know. So as a really, really quick worked example, we're going to have a look at this. So here we've got monochromatic light, in other words, one frequency. It's got a wavelength of 570 nanometers, and it is incident, in other words, it hits. So incident basically just means it's hitting a metal. So it's hitting the metal surface, and it's in a vacuum photocell, which is basically one of those things that we used here. So that's our vacuum photocell. Light causes current to flow through the cell because of photoelectric emission, and this emission can be stopped if we apply a potential difference of 1.25 volts to the cathode. So we make the cathode plus 1.25 volts. We want to calculate the work function of the metal cathode in electron volts, and once we've done that, we want to calculate the maximum kinetic energy that these electrons can have if we then turn our circuit off. So for part A, I want the work function, so I'm going to start off with this particular equation here. So HF's equal to phi plus EK, like that. So that's our standard Einstein equation, and I'm going to rearrange it because I'm wanting the work function. So the work function is equal to HF minus the kinetic energy, like that. But I don't know what the kinetic energy is, but I do know that the maximum kinetic energy is given by the amount of work done by the electric field. So I can say that the work function is equal to HF minus E multiplied by the stopping potential. And now I know all of these numbers. The frequency I can get from the wavelength, h is just Planck's constant, E is the charge on the electron, and the stopping potential I'm told here. So I can put all of these numbers in. So that's h, frequency is the same as the speed of light over the wavelength, and minus EVS. So if I just put all of these numbers in, if we go down here, then I end up with 6.63 times 10 to the minus 34. So that's Planck's constant multiplied by the speed of light times 3 times 10 to the 8, 3.0 times 10 to the 8. So they're things I just get from my data sheet, divided by the wavelength, where the wavelength I'm told in the question is here. So that's 570 times 10 to the minus 9. And then I need to take away the charge on the electron, so 1.6 times 10 to the minus 19. So that's our charge on the electron, again from our data sheet, and multiplied by the stopping potential, and that was 1.25 volts. And if I do all of that, in the end, I end up with a final answer of 1.50 times 10 to the minus 19. to the minus 19 joules. Unfortunately, that's not answered the question because I want this in electron volts. So to convert this into electron volts, I simply divide by 1.6 times 10 to the minus 19, and if I do that, I get 0.92 eV. So that's my final answer. For part B, I then need to know what the kinetic energy is. So I simply go back to this thing. The maximum kinetic energy of these things is equal to HF minus the work function. Well, it's basically exactly the same thing that I've just got. H is Planck's constant. The frequency I can get from the wavelength again, and the work function I've just worked out is this thing here. So again, I'll not bother writing all of those things out, but you can just check. And if you do this on your calculator, you basically end up with 2.0 times 10 to the minus 19 joules, like that. So if you just want to check that you get that when you put your numbers into here, then that's the correct answer. Okay, so that was lots of revision. And you need to, what you really need to be able to explain is A, where wave theory fell down, B, what was observed, C, there are some definitions that you need to know. You then need to know basically why it is that Einstein was able to use the photon model to explain all of these things, and also how you would then measure the kinetic energy in terms of the stopping potential. And then finally, you need to be able to do little questions like this where you basically can take the numbers and you can apply them to Einstein's photoelectric equation. So that was some revision on the photoelectric effect. So thank you very much for watching, and I'll see you again soon.